In this ICFD++ example, we are going to demonstrate file-based mesh morphing in transient simulations. This example problem guides the user through the procedure for using file-based mesh morphing in transient simulations, such as the example shown on the screen of a two-dimensional oscillating ball in a channel. We are going to demonstrate this example using the new Integral Computational Multiphysics Advanced User Interface, or ICMP AUI. Before going into this example, I will briefly cover the new features and components of the ICFD++ AUI for first-time users. For a more in-depth understanding of the ICMP AUI features common across all Metacomp software, please click on the ICMP AUI demo link popping up on the left side of the video, or refer to the ICMP AUI section of your ICFD++ documentation. This ICFD++ interface is composed of the menu bar, where the mouse is currently moving. We have the option to select a menu for opening and closing files and for accessing various tools in ICFD++. The toolbar, which has shortcuts to the commonly used functions and visualization controls, such as fitting the screen to XY, YZ, or XZ views. The canvas, in which a geometry or solution is displayed, and the notebook, currently showing that you are in CFD++ simulation setup mode. Within the notebook, ICFD++ has its action tree or setup wizard, which will guide you logically through the various steps of the problem setup and one or more information trees, in this case the groups and boundary families tree and the boundary conditions tree. Corresponding to each item in the action tree or information tree is its action panel on the left, where the user is given the relevant choices based upon choices made in previous and current panels. All panels are dockable and resizable. We are now going to set up the simulation from scratch using a newly launched AUI. The first panel that comes up is for the working directory. Within the FileMorph example, two subdirectories for two different cases are included. In the first test case, we will simulate an incompressible flow with an oscillating ball in the directory ball2D. We're going to first simulate the problem with the steady-state simulation on the original geometry with the ball in the neutral position. The simulation will then be restarted in transient mode, and file-based mesh morphing will be used to achieve the motion of the ball. Let's start by selecting the steady directory with the original grid files and click OK to accept. We can select No for loading the input file from the current directory, and select Yes to analyze the grid files and read the BC family file. Let's click OK. And this brings up the grid information panel. The grid files have been analyzed, and we can see that we have a total of 19,400 cells, including triangles and quadrilaterals, and 4 boundary selectors for the ball, inlet, wall, and outlet. Let's click OK to close the grid information panel. The next panel that comes up is the cell types and volumes panel. Based on the information analyzed in the previous panel, the AUI has automatically selected quadrilateral and triangle cells as the valid cell types for the simulation. We can click OK to confirm. We now begin the problem setup with the first panel for the general problem definition. The first question asks which option describes the problems you wish to solve. In our case, we're going to be simulating a general fluids problem, so let's select the first option. A number of preset problem classes are also available in ICFD++. We will not be accessing these wizards for this simulation, so we can keep the selection to No and click OK. We're now going to set up more of the specifics of the CFD problem definition. We're going to be simulating an oscillating ball in a channel filled with water. For fluid type, let's select liquid. We are only going to be simulating one species in the system, So for species content, we can keep this selection to single species. Now more details on the nature of the flow. Is the liquid compressible? We're going to select no. Is the flow viscous? Yes. Is the flow turbulent? Yes. And for energy transport, we're going to select no, as this is not important in this simulation. The nature of the simulation type is steady state for this first simulation. So let's select steady state and confirm these settings. At this stage, we are not going to be applying any grid motion or additional specifications. So in this next panel for additional specifications, we can keep the default settings and click OK to continue. We've now reached the equation properties panel. Based on the selection made in the CFD problem definition panel, we can see that the AUI has already selected the incompressible Navier-Stokes equations. Two solution methodologies are available to simulate the case: preconditioning and pressure-based. Both solution methodologies have been tested for this simulation. In this current setup, we're going to simulate the case using the preconditioning solution methodology. For turbulence modeling, we're going to select the default two-equation realizable K epsilon model. And so, to summarize, we're going to be solving the incompressible Navier-Stokes equations. The turbulence simulation type is RANS with the realizable K epsilon turbulence model. Let's click OK to confirm these settings. We are not going to be invoking any additional physics source terms in this simulation, so we can keep the selection for adding physics source terms to no and click OK to continue. This brings up the reference quantities panel. The default is the SI unit system, so we're going to keep to the default for this simulation and click OK. It's important to make sure that the grid is in meters when running with the SI unit system. The fluid properties panel for the primary phase is the next panel. We can see an information set has been created for the incompressible fluid properties. Clicking on this information set and clicking the Edit button brings up the fluid properties that have been applied by default. In this case, water is the default fluid. We're going to be simulating this case using water, so we can click OK to keep this setting. We are going to want to set a base pressure level for the simulation. So let's enter 2.5 E7 for the base pressure and keep to the default value for the bulk temperature of the fluid of 288 Kelvin. We can now click OK to confirm the primary phase fluid properties. The next setting is for the initial conditions of the simulation. Various initialization types are available in ICFD++. The simplest initialization type is setting quantities for the entire domain. More advanced settings, such as setting quantities in XYZ boxes and cylinders, can be selected. For this simulation, we're going to be selecting the entire domain. And let's click the plus button to add a new information set. Clicking on the new information set and clicking the Edit button brings up the primitive variables info set panel. In this panel, let's enter 0 Pascal for the static pressure. The entry for the pressure is the relative pressure, that is the difference between the desired pressure and the base pressure, which is currently set to 2.5 E7. We're going to leave the x, y, and z velocities to 0 meters per second. The temperature has already been set to 288 Kelvin. For the turbulence quantities, we're going to keep the default values and set the values for K and epsilon in a later panel with the turbulence initialization tool. Let's click OK to confirm these initial conditions and click OK to continue to the next panel. We've now reached the Boundary Conditions panel. On the left is the Boundary Families tree with the list of all the boundary families in the computational domain. The second tree is the Boundary Conditions tree with the boundary condition types available in ICFD++. 4 types are available: open, symmetry, wall, and zonal. And within these types, there are many different boundary conditions that can be applied to the simulation. We can also see the boundary families listed in the Groups and Boundary Families tree. Currently, a red cross appears to the left of each boundary family to let you know that no boundary condition has currently been set for these boundary families. Let's start with the first boundary family for the ball, seen in red on the canvas. We're going to be applying a wall boundary condition to this BC, so let's click the ball boundary family and drag it to the wall boundary condition type. We're going to be selecting a viscous wall type with a wall integration type set to wall function. The wall motion type is going to be stationary with respect to mesh motion, and we aren't going to be invoking any additional modifiers. So let's click OK to confirm these settings. We can review the settings in the wall BC that has been created by placing the mouse next to the wall BC1 tag, which summarizes the settings for this BC. We can also see a green check mark has appeared next to the ball boundary family to confirm that a boundary condition has been applied to this BC. Let's now set the inlet boundary condition, which is the green boundary shown on the canvas. This is the inflow condition to the simulation. We're going to be dragging the inlet BC and dropping it in the open boundary condition type. For the boundary condition subgroup, let's select an inflow-only condition. The type of information available will be pressure and temperature, and we are going to apply a stagnation, pressure, and temperature condition. Let's click the plus button to create a new information set, and click on the new information set, and then click the edit button and enter a stagnation pressure of 2E7 Pascal. The turbulence quantities will again be initialized in a later panel. Let's click OK to confirm. Scrolling down, we are not going to be applying any additional modifiers that are shown in this panel, so we can click OK to confirm this setting. We can review the inlet boundary condition by placing the mouse on the OpenBC tag. The next boundary condition is the wall boundary condition, shown in blue on the canvas, and these are the upper and lower walls in the duct. The wall boundary condition has a similar boundary condition to the wall BC, so we can drag the wall BC to the wall BC1 tag, and the wall BC now appears under the wall BC. Both boundary conditions will have the same settings of a viscous wall function integration with no mesh motion. We can now move to the fourth BC, the outlet BC, which is shown in brown to the right. Let's select the outlet BC and drag it to the open boundary conditions type and create a new inflow-outflow boundary condition type. For the boundary condition subgroup, we're going to select an inflow and outflow type. And for the type of information available, we're going to select pressure and temperature using inside velocity. Let's click the plus button to add a new information set. And click on the info set and click the edit button. We're going to select a pressure of 0. Again, this is relative to the base pressure that was set in the fluid properties panel. The temperature has already been set to 288 Kelvin and the turbulence quantities will be initialized in a later panel. Let's click OK to confirm. And click OK to apply this boundary condition. We can now see 4 green checks next to the BC families to confirm that all boundary conditions have been set up. Let's click OK to confirm these boundary condition settings. We now move to the turbulence control panel, where more advanced settings can be applied to some of the turbulence related settings in the simulation. In this simulation, we're going to keep these settings to the default. We aren't going to be using any additional models for turbulence, such as transition, so let's click OK to confirm. We've now reached the turbulence initialization tool, where we can set up the K and epsilon values for all the infosets that have been created within the setup. The 3 infosets relate to the initial conditions, the inlet and the outlet boundary conditions. Clicking on the first infoset, we can review the values of pressure and velocity that was set up in this infoset, and we can see the default 1 and 0.1 for K and epsilon. Let's start by right-clicking the primitive variables infoset to bring up the turbulence calculator. We're going to be inputting a free stream turbulence level of 3e-2, and for the turbulence length scale, we're going to be inputting 2e-4, and we're going to be entering 200 meters per second for the velocity, which is the average velocity that was obtained in the solution. Let's click Compute to generate the turbulence quantities. We can see the K and epsilon values that have been generated and the mu-T over mu ratio of 1:1. This is the turbulence laminar viscosity ratio. Let's click OK and click OK to input these values into the K and epsilon values in the first information set. We're going to be using the same turbulence quantities for the other information sets, and we do not need to recalculate the quantities. We can use the Copy Information Sets feature and start with the source turbulence quantities from the primitive variables infoset and copy them to the stagnation pressure infoset and pressure temperature information sets for the inlet and outlet conditions. Let's click Apply to copy these values and click OK to continue. We can now review the 2 information sets and see that the turbulence quantities have been input into these 2 information sets. Additional information that's available in this panel is quite useful, and this is the computed infoset density and computed infoset viscosity in the simulation. Let's click OK to move to the next panel. We are not going to be using the help set numerics feature in ICFD++, so we'll click OK to move to the next panel. We've now reached the Riemann solver settings. And since we are using the preconditioning algorithm, let's click plus to open up the preconditioning controls, and also let's open the advanced preconditioning controls. Firstly, for the approximate system velocity, which is an important parameter to input, typically this is the average system velocity, we're going to be inputting a value of 200 meters per second. We're also going to be activating pressure acceleration. We'll use the default acceleration factor, and we're going to be changing the fraction of the maximum velocity from 0.05 to 0.25. These are best practice settings for these simulations, which were determined in advance. We can now click OK to confirm the Riemann solver settings. We now move to the Simulation Strategy and Integration panel. In the CFD problem definition panel, we had opted for a steady state simulation. We're going to be simulating the case from the start, so the is the restart can be set to no. Let's select 750 for the number of global steps for this run, and we can keep the orders of magnitude convergence to the default 5. Let's click OK to confirm these settings. We now move to the second time integration control panel, and we're going to be selecting to ramp the courant number for the local time step from a value of 1 to 100 from step 1 to 100. The other settings can be left to the default, and let's click OK to continue. The spatial discretization panel is automatically set to second order inviscid discretization and a 2D dimensionality of polynomial using the XY coordinates. We can keep these settings to the default and click OK. The next panel that comes up is the neutral plot file options, which controls the output variables that are written to the solution file. Several options are available for pressure, temperature, velocity, turbulence quantities, surface quantities, and so on. For this base simulation, we're going to keep the default output variables such as pressure, temperature, density, and velocities. And let's click OK to confirm. A pop-up window with a message asking to write these options to the neutral plot file and also to copy the neutral plot file options to the plot output options file. Let's choose to write to both of these files to confirm these output options and click OK to move to the next panel. We've now reached the probe and output files panel, where we can control the frequency of output of the solution file. The default is 200. We can keep this value to the default and click OK to continue. We can now save the input file and run CFD++. We can choose a double precision mode to run the simulation and using single CPU, and click OK to launch the simulation. The solution is in progress, and we can see output information is printed at every time step. The solution files are being written in the working directory. We will now move to the transient simulation. Let's now start the setup for the transient simulation. First, copy the mesh and solution files from the steady directory to a new directory called transient. I'm now in the transient directory, and I'll click OK to continue. Now the transient simulation will be restarted from the steady state simulation, and I will load the input file from the steady state simulation. At this stage, there's no need to reanalyze the grid files, so we can keep that selection to no, and click OK. We've now loaded the input file for the steady state simulation that was created in the previous section of this example. The grid does not need to be analyzed. The grid boundaries should appear similar to the steady state case as shown on the canvas. And we are starting the setup with the steady state simulation, hence only the panels that need to be changed will be discussed. Let's start with the CFD problem definition panel. In this panel, earlier we had selected to simulate a steady state case. Let's now change that to a transient simulation and click OK. Let's confirm the equation properties settings. We're going to be simulating using the preconditioning algorithm and with the two equation realizable K epsilon model. Let's confirm these settings. Based on the changes made in the CFD problem definition panel, we can see a number of crosses appear in the action tree for panels that we need to address. Let's click OK to bypass the help set numerics and move to the simulation strategy and integration panel. We can see that dual time stepping has been activated. We are going to be selecting a restart from the steady state solution, and let's select 600 global time steps for the simulation and click OK to move to the next time integration control panel. We're opting to not load default settings for the transient mode, so keep this selection to no and click OK to continue. We now move to the next time integration control panel. We are going to be choosing no for the global time step based on courant number computation, and for the spatially varying local time step, we're going to select yes. For the courant number for local time step, we're going to ramp this from 50 to 50, thus keeping it constant, from step 1 to 100. Let's select a value of 1e minus 6 seconds for the global time step size, with the maximum number of internal iterations set to 15 to ensure good convergence of the inner iterations. One cycle of the ball motion is completed in 12e minus 5 seconds, as we have specified in the grid motion file. With a global time step size of 1e minus 6 seconds, one cycle of the ball motion will be completed in 120 steps. One cycle of the ball motion means the ball moves up and down and back to its original position. We will be simulating 5 cycles of the ball motion in 600 time steps. Let's now set the order of global time stepping to second order and click OK to confirm these time integration settings. We can click OK to keep the neutral plot file variables to the same as in the previous simulation. Now let's go back up to the Additional Specifications panel. We now want to apply grid motion in the simulation. Let's click Yes to activate grid motion. 2 further options are shown: 6-DOF based motion or other types of motion. Let's click Yes for other types of motion and click OK to continue. We've now reached the grid motion specification panel. We see 2 trees on the left on the action panel, the groups tree and the grid motion types tree. In the grid motion types tree, we can see various options for grid motion that can be applied to the simulation, such as general file-based translational motion or translational rotational motion. We see 3 options for mesh morphing. The file-based mesh morphing options are a legacy mode that can be applied to groups and boxes in the domain. The combined file and BC-based mesh morphing mode is a new mode for mesh morphing, which uses both a file-based and a BC-based method for improved efficiency of the setup. What we need to do is to select the groups from the groups tree and drag them to a grid motion type. In this case, let's select the All Groups option and drag it to the combined file and BC-based mesh morphing type. This brings up the combined file and BC-based mesh morphing menu. Let's start by ignoring the file-based controls usage and applying the BC-based controls usage. We now see the option for BC front fitting specification. Let's press the green plus button to add a new information set under BC front fitting. Now we have 4 BCs in the simulation. What we are going to do is apply grid motion to the ball BC. However, we also want to specify anchor points for the 3 other BCs. This means the code will force the displacements at these BCs to 0. Let's create 4 BC front fitting specifications, 1 for each BC. Now let's click on the first one, BC front fitting, and click the Edit button and select the first boundary family for the ball. For this BC, let's go to the front fitting type, and we can see various options for front fitting, such as a BC linked to an average speed or a user specified tangential component. All of these motion types are documented in the user manual. For this simulation, let's select file-based, translational, displacement versus time. That is, we are going to be using a file to specify the translational displacement versus time for the motion of the ball. This BC front fitting type requires an information set, so let's click the green plus button to add a new information set. And let's click on the information set created for Mesh Morphing BC speed file. And we can see the default file name of simplemotion.dat. The simplemotion.dat file has already been created and can be found in the example files in the transient directory. Inspecting the simplemotion.dat file, you will see that the first 4 lines of the file are the headers, which include time intervals, number of columns, and interpolation type, after which has been specified the time and XYZ displacements for the ball motion. Let's click OK to confirm the setting. Now let's click on the second BC front fitting, edit, and select 2 for the inlet BC, and we can keep the front fitting type to type 0, which automatically sets this BC to an anchor BC. Let's click OK. Let's now apply a similar setting to BC3. Let's click on wall and leave the front fitting type to type 0. And then the final BC for outlet, and keep the front fitting type to 0 and click OK. We've now set up all the BC front fitting specifications. Additional options here are available to restrict morphing by cell groups or XYZ boxes and avoiding interpolation based on a coordinate. We will not be invoking any of these advanced options, and we can click OK to confirm the setting. We can now click OK to apply these grid motion specifications. The next panel that comes up is the overall grid motion control panel. By default, the AUI has selected to turn on the defined velocities. Let's keep to this setting. AUI has also applied move grid with the selected velocities. We want to keep the setting active. This is a small case. For larger cases, there is the option to activate multi-CPU morphing in this panel. We will run this simulation using single CPU morphing. Let's click OK to confirm these settings. Let's go back for a moment to the probe and output files. And let's activate the solution file with step number appended to its name. And we can select to output solution files at every 10 steps so that we can capture the motion of the ball. And let's click OK to confirm. We can now save the input file and run CFD++ in double precision mode and using single CPU, and let's click OK to launch the simulation. The simulation is in progress, and we can see from the output that the RBF algorithm is outputting some values, such as the starting iterations and the convergence error. The solution files are being written in the working directory, the transient directory. The post-processing and solution analysis of this simulation will be conducted in another video. Thank you. In this next case, we simulate a NACA 12 airfoil with flap deflection and employ mesh morphing to achieve the deflection of the flap. Let's start by selecting the flap 2D subdirectory as the working directory and click OK. We can select Yes to analyze the grid files and Yes to read the BC family file. Let's click OK. And this brings up the grid information panel, which summarizes the number of elements in the grid and also the number of boundary selectors, in this case 4. Let's click OK to close the information panel. And let's zoom in to the grid on the canvas and take a closer look at the configuration of the airfoil and the flap. We have the airfoil shown in green, the flap section shown in blue, and there's an additional boundary called the trailing edge, and if we zoom in to the end of the flap section, we can see the trailing edge boundary. A boundary condition needs to be applied to this BC. In the first simulation, we will simulate a steady-state case of low-speed flow over the NACA 12 airfoil with a stationary flap at 0 degrees angle of attack. A rapid problem setup is achieved using the Aerospace Wizard within CFD++. The simulation will then be restarted in transient mode, and file-based mesh morphing will be used to achieve flap deflection of 10 degrees in the positive and negative direction. Based upon the selections made in the previous panel, the AUI has automatically selected quadrilateral and triangle elements as the valid cell types for this simulation. Let's click OK to confirm this setting. We now move to the general problem definition, and the first question asks which option describes the problems you wish to solve. Let's select the General Fluid Problems option. And let's also select Yes to access the preset problem classes or wizards in CFD++. This brings up a new menu for the wizard type, and we can select either the external aero or external auto wizard. Let's select the external aero wizard for fast setup of external aerodynamic flow simulations, and let's click OK. We've now reached the external aero wizard panel. We can make several selections in this panel, and the wizard will quickly set up many aspects of the simulation. Let's start by selecting the SI unit system. For the type of input to be provided, we can select Mach number altitude, or Mach number Reynolds number temperature, or primitive variables. In this simulation, we are going to initialize the wizard with Mach number Reynolds number and temperature inputs. Let's input a free stream Mach number of 0.15, a Reynolds number of 1.76 E6. Note that the grid supplied has a 1 meter chord. We use the default temperature value of 288 Kelvin. The angle alpha is in the XY plane, so let's just select XY for this option. However, we are not going to be inputting an angle of attack, so we can keep the pitch angle to 0 and also the Y angle to 0. Let's move to the turbulence quantities and input a turbulence intensity of 0.02 and a turbulent laminar viscosity ratio of 50. With these inputs, we can activate the wizard to set up several aspects of this problem. Let's click the plus button to show the steps that the wizard is going to take. Firstly, the wizard will set the equation type to compressible perfect gas Navier-Stokes. However, in this case, the free stream Mach number is very low at 0.15, and so the preconditioning option will be activated. The wizard will initialize the domain with the given quantities and set up the K and epsilon values in the information sets, and the wizard will set up air as the working gas in the fluid properties panel. Initial time integration quantities will also be set up. Let's click OK to proceed. A message pops up saying the Aero Wizard is complete. Let's click OK to close this message. Now looking at the action tree, we can see that many panels have now been set up. Let's quickly review these panels, starting with the CFD problem definition. We have a single species gas simulation, mostly below Mach 0.5, and we're going to start with a steady state simulation. At this stage, we have no additional specifications. In the equation properties, we are solving the compressible perfect gas Navier-Stokes equation set using the preconditioning solution methodology and the two-equation realizable K epsilon model. No additional physics source terms have been added. We've set up the reference quantities. The fluid properties have automatically been set to air. The initial conditions have also been set up based on the Mach number, Reynolds number, and temperature that was input into the wizard. We can see the static pressure and x velocity that has been set up by the wizard, and the k and epsilon values as well. At this stage, the boundary conditions still need to be set, so let's go to the boundary conditions panel. Starting with the outer BC, for the far field condition, let's drag the outer boundary family and drop it to the open boundary condition type. We're going to be selecting an inflow and outflow boundary condition, and the type of information available is the primitive variables, and for the condition type we're going to set characteristics based, typical for a low-speed far-field condition. We can see that there are existing information sets that have been created by the wizard for the initial condition. Let's select the primitive variables 1 information set, and let's review the information. We have the static pressure and static temperature and x velocity in the information set, as well as the k and epsilon values. These values correspond to the initial condition set. Let's select them for the far field condition and click OK. We can now see a green check appear next to the outer BC family name in the groups and boundary families tree, confirming that a boundary condition has been set for that BC. Let's now move to the airfoil surface, shown in green on the canvas, and let's drag the airfoil boundary family name and drop it to the wall boundary conditions type. Let's select a viscous wall type with a solve-to-wall wall integration, which is appropriate for the grid that we are using. And we're going to select an adiabatic wall heat transfer type. We are not going to be invoking any additional options, and we can click OK to confirm the setting. The flap and trailing edge boundaries also have the same boundary condition type as the airfoil. So for the flap boundary, we can simply drag the flap boundary name and drop it to the wall BC1 that was created for the airfoil, and we can see the flap BC now listed under the wall BC1 type. Let's do the same for the trailing edge BC. Drag and drop it to the wall BC1 type, and we can review these settings, viscous, solve-to-wall, and adiabatic, for all 3 BCs. We've now set up all the boundary conditions for the simulation. We have 4 green check marks. Let's click OK to confirm these settings. We can now save the input file and run the steady-state simulation in double precision mode using a single CPU. Let's click OK to launch the simulation. The simulation is in progress, and the solution files are being written in the working directory. We will let the simulation continue until convergence, and then set up the next stage of the simulation, which is the transient simulation with mesh morphing. So once the steady-state simulation has completed, we create a new directory called transient and copy all files to the transient directory. Let's now move the working directory to the transient directory and click OK to continue. We can load the input file that was created for the steady-state simulation. At this stage, it is not necessary to reanalyze the grid files, so let's click OK to continue. So we are starting with the setup of the steady-state simulation, hence only panels that need to be changed will be discussed. Let's start by going to the CFD problem definition panel. We're now going to be running a transient simulation to simulate flap deflection using mesh morphing. So let's change the nature of simulation to transient in this panel and click OK. Let's go back to the additional specifications panel and select yes to apply grid motion. This brings up two further options: activating 6-DOF-based motion or other types of motion. For mesh morphing, select other types of motion and click OK in the additional specifications panel. We're still going to be computing this simulation using the compressible perfect gas Navier-Stokes equations, using the preconditioning solution methodology and the two-equation realizable K-epsilon model. Let's click OK to confirm the setting in this panel. And we now move to the grid motion specification panel. On the left, we can see the groups tree, and the second tree is the grid motion selected tree, which displays various options for grid motion that can be invoked in a simulation, such as file-based translational motion and mesh morphing options. Within the mesh morphing options, we can see file-based mesh morphing by groups, file-based mesh morphing by XYZ boxes, and the new mode for combined file and BC-based mesh morphing. We're going to run this simulation using the file-based mesh morphing by groups option. Let's click all groups from the groups tree and drag it to the file-based mesh morphing by groups. This brings up a panel. In this panel, we can specify the grid motion file. Let's browse the directory and pick up the gridmotion.bin file. It's important that the binary version of the file is selected. In this example, we have pre-prepared the grid motion file for the user. Let's take a quick look at the hint on this panel by clicking the plus button. This displays the file format of the grid motion file. Let me discuss the contents of the grid motion file in some detail. The first step is to determine which boundaries in the morphing simulation are to be used as control points. Generally, these points will include the nodes on the boundary that is moving, and it is also necessary to specify anchor points in the domain where control points are specified with 0 displacement. In this example, the strategy is to use all nodes on the flap boundary as motion points. In addition, all nodes on the airfoil surface will be specified as anchor points with 0 displacement. This is important because the airfoil surface is very close to the flap, and we want to make sure that the airfoil nodes stay fixed while the flap is moving. The trailing edge nodes have also been included with the motion control points of the flap boundary. Care must be taken when specifying the node points at edges of two adjacent boundaries, because the mesh morphing algorithm does not allow the use of repeated control points. So, for example, a node at the edge of the trailing edge and flap boundary cannot be repeated in the grid motion file. The nodes on the outer BC were also used as anchor points with 0 displacements. So once we've selected the number of control points, we can enter the final number of control points in the first line. The second line is the number of time intervals in the file. We can then list the control points, the X, Y, Z's of the control points, followed by time 1 and the displacements and velocities associated with the control points at that time. So in this example, we selected 4 time intervals. At t equals 1 at 0 seconds, at the start of the simulation, all displacements and velocities were set to 0. At t equals 2, which is at 3e minus 2 seconds in the simulation, the flap has deflected 10 degrees upwards, and all control points on the flap and trailing edge are specified with the rotated values for the displacements and the corresponding velocities. All displacements and velocities at anchor points at this stage are set to 0. At t equals 3, which is at 9e minus 2 seconds in the simulation, the flap has deflected 10 degrees downwards, and all control points on the flap and trailing edge are specified with the rotated values and corresponding displacements, with the rotated values for the displacements and the corresponding velocities. The displacements and velocities at the anchor points are set to 0. Finally, at t equals 4, which is at 12e minus 2 seconds in the simulation, the flap has returned to its original position. An interesting feature of this mesh morphing mode is that there is automatic periodicity of motion, so that only the complete cycle need be specified in the motion file, and the motion is repeated as further steps are computed. Hence, the flap deflection will continue as long as the simulation continues. Let's click OK to close this panel. We've now set up the gridmotion.bin file with the mesh motion, and we can click OK to continue. We've now reached the overall grid motion control panel. Some additional specifications need to be made here for mesh morphing. We need to make sure that turn on defined velocities is set to yes. We need to make sure that move grid with selected velocities is also set to yes. We are going to move the grid in a mesh morphing simulation. If we wanted to invoke multi-CPU morphing for improved efficiency of a larger case, we could activate multi-CPU morphing in this panel. In this case, we're going to simulate the case with single CPU morphing. Once we've made the selections in this panel, we can click OK to continue. We now move to the Help Set Numerics panel. We're not going to be needing assistance in setting numerical parameters, so let's click OK to continue. We can click OK to move past the Riemann Solvers panel, and we arrive at the Simulation Strategy and Integration panel. So we are going to simulate a restart in transient mode. So let's click yes for a restart. We're going to select 600 time steps for the simulation, and we can see that dual time stepping is activated. Let's click OK, and do not choose to load default settings for the transient mode. And we can now move to the time integration control panel. Let's set the global time step based on courant number to no. And we're going to keep the spatially varying local time step. For the courant number for the local time step, let's select 50 for both options. This will set up a constant local courant number, but will allow the courant number to be slowly ramped back up if ACAPs occur. And we can keep the setting for the step numbers from 1 to 100. Let's set the global time step size to 2e-4 seconds and a maximum of 15 internal iterations for improved convergence of the inner iterations in the transient simulation. Let's set the global step inner iteration termination criterion to 0.01 and the order of global time stepping to second. With a global time step size of 2e-4 seconds, one cycle of the flap deflection will be completed in the 600 steps that we are going to simulate. Let's click OK to accept the time integration control settings, and we now move to the neutral plot file options. We're going to keep to the default selections of pressure, temperature, and velocities for the outputs. We can also look at the turbulence outputs and make sure that kinetic energy and dissipation have been activated, and also Y+ for the surface. Let's click OK to confirm these settings and save these to the neutral plot file output options. One additional selection is let's go back to the probe and output files. Since this is a transient simulation, we want to save the solution files at intervals. So let's select the NPF with step number appended to the name, and we're going to select 10 for the frequency of output, so that every 10 steps we will write a solution file in the simulation. We will need these intermediate solution files to create an animation of the grid motion and solution. Let's click OK to confirm these settings, and we can save the input file and choose to run CFD++ in double precision mode using a single CPU and launch the transient simulation. The simulation is in progress, and we can see some output related to the mesh morphing is being printed, such as the RBF initialization and RBF converged error. We will let the simulation continue running and then post-process and analyze the solution files in a separate video. Thank you.